On page 20, we're going to look at the structure of some cations, anions, and neutral atoms. This page is really important. Don't gloss over it. There are many things you are asked to memorize in organic chemistry, like nomenclature, functional group structures, and names. But electron positions, electron transfers are crucial to understanding organic chemistry, and this is where we start. We'll be going over this many times in many ways, so if we don't get it all right now, don't fret, but give close attention here. Let's start with some second period elements like boron. Boron's Lewis symbol shows 3 dots. It has 3 valence electrons. Typically forms 3 bonds, and after bonding it has no unpaired electrons. So we'll give this generic structure a specific identity. Let's put hydrogens on here. This is borane, BH3. You can see that it's sp2 hybridized. It only has 6 electrons in the valence shell. It's subvalent. It has an unhybridized 2pz orbital. That makes it electron accepting. An electron acceptor is an electrophile, electron lover. We use the symbol E+. Even though it may not be positively charged, we use the symbol E+, electron accepting. Let's react this with a strong base. I'll use sodium hydride. Now, sodium hydride is a really strong base. Its pKb is -21. So this is our nucleophile or electron donor. And so the electron donor donates a pair of electrons to the electron acceptor. We used curved arrows to show the transfer of electrons from the electron donor to the electron acceptor, and that's called a reaction mechanism arrow. And when that occurs, we'll form the structure you see on the right. We'll put in some hydrogens here. This would be formed. And the compound as a whole would look like this: Na+, BH4-, and that's sodium borohydride. But within the borohydride anion, we see that boron itself is an anion. How many electrons does it own? Half of what it shares. It owns 1, 2, 3, 4. For a group 3A atom to own 4 electrons, it must be negatively charged, and so it's called a boride ion. We've already discussed carbon in a previous video, so I won't spend time with that here. Let's move to nitrogen. Nitrogen is in group 5A, therefore it has 5 valence electrons, 3 unpaired electrons, and 1 pair. Nitrogen commonly forms 3 bonds, and after bonding, as we see in the central structure, it has 2 unshared electrons. Let's take a simple example, and let's say this might have been ammonia. Now, ammonia is a moderately strong base. Its pKb is 4.8. If it reacts with an acid, such as a hydrogen ion, it can donate its unshared pair of electrons to the hydrogen ion, and that will form the structure we see on the left, which is ammonium ion. Now, within the ammonium cation, we see the nitrogen is actually a cation. How many electrons does it own? Half of what it shares. 1, 2, 3, 4. That's 1 less than 5, and therefore it's a cation. This cation is called a nitronium cation. The IUM ending that we use for ammonium implies positively charged. It's also true in nitronium. Now, ammonia can also be an acid. That's probably not something you're familiar with. It would be a very weak acid because it's very difficult to remove those hydrogens from something that's basic, but its pKa is measurable. It's 35. To remove a hydrogen ion from ammonia would require a really strong base. We're going to use again sodium hydride because it's such a strong base. Sodium hydride can remove one of these 3 weakly acidic hydrogens. H+ leaves and the pair of electrons stays behind, forming the structure we see on the right. If we put some hydrogens in there, that anion is called amide. the structure we would have formed would be sodium amide, and some hydrogen gas would be liberated when the H- picks up H+. But I want to focus on the amide anion. Within the amide anion, the nitrogen is negatively charged. Count the electrons that it owns. It owns 2, 4, 5, 6. That's a group 5A element with 6 electrons, so it's an anion, and we call that nitride ion. Now I realize there's ambiguity here, because in inorganic chemistry, this compound is called sodium nitride, and in it, nitrogen is -3, whereas in this compound amide, the nitride ion is -1, but it is what it is. It's an ambiguity. Let's look next at oxygen. Is in group 6A. It has 6 valence electrons, commonly forming 2 bonds and then having 2 pairs of unshared electrons, as we see here in the center. Let's give it some identity. Let's say it's water. Water is a weak base. Its pKb is approximately 16. If we reacted with an acid, let's say for example hydrogen ion, it can donate a pair of electrons. Let's take this pair right here, forming hydronium ion, which we see on the left. Within the hydronium ion, we see the oxygen is actually a cation. We know it's cationic because it owns 2, 3, 4, 5 electrons, 1 less than 6, and therefore it's positively charged. A positively charged oxygen cation is called an oxonium ion. Well, water is amphoteric. It can also act as an acid, and it's just as weak an acid as it is a base. Its pKa is about 16. Let's react it with our really strong base, sodium hydride, and let's put some hydrogens on here. So a really strong base reacting with this weak acid. The base donates a pair of electrons to the hydrogen ion. The pair of electrons stays behind, and we form the structure on the right, which you may recognize as hydroxide. Within the hydroxide ion, we have an oxide anion. How many electrons does it own? 2, 4, 6, and 1 is 7, which is why it's negatively charged. We call that an oxide ion. Again, look at the ambiguity. What is this called? This is sodium oxide, and we call O-2 oxide, but we also call oxide O-1 within the hydroxide molecule. Let's look at fluoride, group 7A. 7 valence electrons, commonly forms 1 bond. After bonding, it will have 6 non-bonded electrons, 2, 4, 6. Now, fluorine being the most electronegative element, there's no case where some other atom or species could withdraw electrons from it. It's not going to form a cation, but it could form an anion quite readily. Take the case of hydrogen fluoride. Hydrogen fluoride is a moderately strong acid. Its pKa is 3.2. We can react it with a base. Let's take something more familiar, like hydroxide. The hydroxide is the electron donor. Hydrogen ion is the electron acceptor. This pair of electrons has to stay behind. It can't go with the hydrogen. And that gives us the structure on the right, which is a fluoride anion. Notice that in the fluoride anion, fluorine owns 2, 4, 6, 8 electrons, which is why it's negatively charged. Take a look at chlorine. Similarly, chlorine can be bonded to hydrogen, in which case it's an acid. This is a strong acid. The pKa is -7. If it reacts with a base such as hydroxide, it's deprotonated like so, and we get chloride anion. Now, chlorine is not the most electronegative element, so there are cases where it could actually be an electron donor. Now, we'll cover specific examples of this later, so we'll use a generic one for here. Let's just say that this is not HCl, but let's say, for example, it's actually chlorine, Cl2. Now in chlorine it's got non-bonded pairs of electrons, and if it was to react with something that was electron accepting, and we'll see examples of that, then the chlorine could donate one of its pairs of electrons to the electron acceptor, the electrophile. That being the case, we'll have the structure on the left. So the central chlorine ion is positively charged. How many electrons does it own? 2, 4, 5, 6 instead of 7. This is called a chloronium ion. Now, whatever is said about chlorine can also apply to bromine and iodine. So again, this may seem strange, but give it your best. We'll be doing this type of rationalization many times in organic chemistry. It's the key to understanding it. Page 21, 3 types of unsaturation. In a previous video, you were introduced to unsaturated hydrocarbons, alkenes, and alkynes. And recall that unsaturation means that compounds have pi bonds to which more atoms can be chemically added. But unsaturation is not restricted to hydrocarbons. For example, this is a ketone. Made of carbon, hydrogen, and oxygen, and it has unsaturation. It has pi bonds in it. The relative position of the pi bonds in a compound affects a compound's behavior in a chemical reaction. And there are 3 cases to consider, or 3 types of unsaturation. First, let's look at conjugated unsaturation. The word conjugated means related. So conjugated unsaturation occurs when we have an alternating pattern of sigma and pi bonds, as for example in 1,3-butadiene. We have pi, sigma, pi. That's the alternating pattern. In 2-cyclopentene, we have sigma, pi, sigma, pi. Again, this alternating pattern of sigma and pi bonds. In a conjugated molecule, a reaction that begins at one end of a conjugated system can actually move all the way across the conjugated area and finish up at the other end. This is understandable if you look at the orbital diagram of a conjugated system. So this is the orbital diagram of 1,3-butadiene. The carbon-to-carbon pi bonds between the first and second carbons are actually the overlap of unhybridized 2pz orbitals on the first carbons. Likewise, the pi bond between the third and fourth carbon are represented by the overlap of the 2pz orbitals on the third and fourth carbons. But what about the second and third carbons? Notice that their 2pz orbitals are, well, they're adjacent to each other in the same way that other pz orbitals are adjacent. And so why can't electrons in these orbitals overlap all the way across? And in fact, that's what happens. The p orbitals overlap across all the carbons in a conjugated system, and so reactions that initiate at one end can wind up finishing at the other end of the conjugated molecule. The second case to consider is isolated unsaturation. That occurs when pi bonds are separated by more than one sigma bond. As for example in 1,4-pentadiene, we have the pattern pi, sigma, sigma, pi. So these are separated. Or in 3-cyclopentene, we have pi, sigma, sigma, again, pi. Look at the orbital diagram. The pi bond in the first 2 carbons, represented by the overlap of these 2pz orbitals, are separated from the pi bond on carbons 4 and 5. They're separated by 2 sigma bonds, and so any reaction that occurs on one pi bond is completely isolated or insulated from what's occurring on a second pi bond. Third possible case is cumulated unsaturation, as in the case of 1,2-butadiene. Here, 2 pi bonds are attached to the very same carbon. They're accumulated. Now, this arrangement is not very stable, and these compounds are only encountered occasionally, and we'll deal with them when they arise. So that's it for page 21. 3 types of unsaturation: conjugated unsaturation, alternating pattern of sigma pi bonds; isolated unsaturation, pi bonds are separated by more than one sigma bond; and cumulated unsaturation when pi bonds are stacked on the same carbon. Page 22, resonance. Resonance is another tool in the toolbox of the organic chemist. So electric charges in an organic molecule indicate a high energy and reactivity in the compound. You see, carbon and hydrogen are unstable, or they are reactive when they're charged. Reaction intermediates or transition states are often charged and thus represent the highest energy level of a chemical reaction. The higher the energy of a transition state, the greater is the activation energy of a reaction. It's like an energy hill that has to be climbed by each molecule before reaction can occur. And hence, the higher the energy hill, the slower the reaction proceeds. Now, resonance is a means by which electric charge of an atom is spread out, or we say delocalized, over several atoms in the molecule. And the effect of this charge delocalization in a reaction's transition state is to decrease the activation energy, and thus will speed up a reaction. So the chemical reactivity of many conjugated unsaturated compounds is enhanced by their ability to delocalize charge via resonance in a transition state. The more resonance structures you can draw, the greater the charge delocalization and the lower the energy hill. And so you, as a student, need to become skilled at drawing resonance structures of organic molecules. And you know what? It's a way of understanding how a reaction works and successfully predicting the products. There are, in fact, 3 rules for resonance. You don't need to memorize the numbers, but you should remember the 3 processes. So the first case here, we have a non-bonded pair of electrons that becomes a pi bond on top of a sigma bond, provided that it's all connected to the same atom. Pi bond formed from a non-bonded pair of electrons. Now when this occurs, the charge of the central atom must change by 1 because it owns 1 less electron. So for example, this atom owns 4 electrons, and after resonance it only owns 3. That's why the charge goes from neutral to +1. If this atom was negative to start with, then after moving an electron over, it would become neutral. Rule number 2 is the exact opposite of rule number 1. A pi bond that's directly connected to an atom can become a non-bonded pair of electrons on that atom. So now the atom gains an electron and its charge will become more negative by 1. In this case, this atom owns 3 electrons and is positively charged. Now it owns 4, so it's neutral. Rule number 3, the simplest of all, is simply that a pi bond can flip from one side of an atom to the other side. Now when this occurs, there's no change in charge. All of these electron movements require that the electrons stay attached to the same atom, and thus it's a small energy change involved. Here's how we draw resonance structures. First of all, resonance structures are placed inside square braces, and the resonance structures are joined by two-way arrows. This is not the equilibrium arrow. Consider the first case. A carbocation, immediately attached to an aromatic ring. This is called a benzylic carbon. It happens to be a carbocation. This pi bond, which is directly adjacent to the carbocation, using rule number 2, can flip over to the other side of that carbon. And in so doing, the carbocation is now neutral and the carbon charge is now moved into the ring. So let's number these ring positions. That's position 1, 2, 3, 4, 5, and 6. So we see number 2 carbon is now sharing the positive charge along with the benzylic carbon. This process can continue. We have another pi bond that can flip over, neutralizing that positive charge, and now the positive charge is in the number 4 position. So now we have a positive charge delocalized or spread over 3 carbons. It becomes less reactive, more stable. And of course this can happen one more time, and now we have a positive charge in the number 6 position. So now we have a positive charge spread over 4 different carbons. So when a positive charge is on a carbon next to a conjugated system, that positive charge can be delocalized. This lowers the energy of the transition state and makes that structure a little more reactive than it otherwise would be. The same is true if that benzylic carbon is an anion. Using rule number 1, a non-bonded pair of electrons can become a pi bond attached to the same atom. Now, if that's going to happen, then this pi bond in the ring has to break. Otherwise, this carbon right here would have 5 bonds, and it can't have 5 bonds. So at the same time as rule number 1 is occurring, we see that rule number 2 is occurring. The pi bond becomes a non-bonded pair on an adjacent carbon atom. So what's happened here is our negative charge has been delocalized or spread out over the benzylic position and carbon number 2. Now this process can continue. The non-bonded pair of electrons becomes the pi bond. At the same time, a pi bond breaks, becoming a non-bonded pair of electrons. And now we see the negative charge is spread out over 3 carbons. And this can occur one more time. And now we have the negative charge on the number 6 position. So by virtue of resonance, our negative charge in the benzylic position has now been delocalized or spread out over 4 different locations. This lowers the activation energy of that intermediate. It will make this reaction go faster than if that aromatic ring was not attached. Let's take a simpler example. This is not a ring, but it is conjugated. Here we have a carbocation adjacent to a pi bond. Following rule number 3, a pi bond can flip from one side of an atom to another, and in doing so, the carbocation on the right is neutralized, and that creates a carbocation on the left. So now our positive charge is delocalized over 2 different positions. By way of a caveat, I must tell you that resonance structures are admittedly not exactly correct. That is, electric charges do not exist in different locations at different times, but rather the electric charge is continuously shared by all the contributing atoms. So these resonance structures are not exactly true, but the structures that show distinct and different charges turn out to be very useful in explaining why and where reactions occur, as you will see. And so we choose to overlook the imperfections of this resonance model in view of its usefulness. Page 23, the stability of carbocations. Take a look at these carbocations. They differ in the number of alkyl groups attached to them. The carbocation on the far right is named a methyl carbocation. It's a methyl group in which the carbon is a carbocation. This is a primary carbocation. The carbocation is bonded to one other carbon group or alkyl group. A secondary carbocation is one in which the carbocation is bonded to 2 carbon groups or alkyl groups. And a tertiary carbocation is one in which the carbocation is bonded to 3 alkyl groups. The more alkyl groups you have on the carbocation, the more stable, the less reactive the carbocation becomes. So, what is it that causes alkyl groups to stabilize carbocations? Somehow they must be donating electron density to this electron deficient carbon. There are 2 theories proposed for how this happens. One is called the inductive effect, which basically says that alkyl groups covalently bonded to a carbocation act as if the bond was polar. And why not? Could it not be that the carbocation is more electronegative than a neutral carbon, and therefore these electrons in the covalent bond spend more of their time closer to the electron deficient carbocation? The more alkyl groups you have attached to the carbocation, the more electron density moves towards it. Simple and reasonable. So alkyl groups stabilize carbocations by inductive effects. The other argument is called hyperconjugation. Take a look at this carbocation. It's sp2 hybridized. It has 3 sigma bonds and an empty 2pz orbital. Now, any alkyl group attached to it has at least one of its 3 bonds that are in line with the 2pz orbital. whether this is to carbon or to hydrogen, it can line up and overlap to some extent with the empty 2pz orbital. So again, it donates electron density toward the electron-deficient carbocation, but this time not through the sigma bond, but rather through the pi or p orbital system, and that is called hyperconjugation. So both of these two factors, inductive effects and hyperconjugation, contribute to the stability of carbocations. The more alkyl groups we have, the more electron donation can occur to the carbocation. And that'll be it for this lecture.